We know the universe operates on rules. Precise, immutable, mathematically perfect rules. And for the last 400 years, we've gotten very good at writing them down. But in the last few decades, a handful of measurements have surfaced that don't just challenge those rules, they suggest the rules themselves are a kind of cosmic placeholder. Because if you take these 10 findings at face value, the only logical conclusion is that this universe, the one we're standing in, the one with stars and planets and conscious beings asking this question, should not by any known law of physics exist. And before you dismiss that as hyperbole, let's start with the one that forced Nobel Prize winners to question whether reality is locally real. But to understand why that matters, we need to start with something that's been quietly broken since the beginning of time. Alright, let's go. Number 10. The vacuum catastrophe. In 1916, when Einstein published his general theory of relativity, he introduced a term into his equations called the cosmological constant. He later called it his greatest blunder. But in 1998, two independent teams, Adam Ries and Saul Perlmutter leading one, Brian Schmidt the other, measured distant Type 1 supernovae and discovered the expansion of the universe isn't slowing down. It's accelerating. The cosmological constant was back. But when quantum field theory predicts the energy density of empty space, it doesn't get a small number. It gets the largest number in physics. Quantum mechanics says the vacuum of space should be seething with virtual particles popping in and out of existence, each contributing to a vacuum energy density. When you calculate it using standard quantum field theory, you get a value about 120 orders of magnitude higher than what the observed cosmological constant measures. That's a 1 with 120 zeros after it. That's not a rounding error. That's the biggest mismatch between theory and observation in all of science. It means either quantum field theory or general relativity, or both, are wrong in ways we haven't begun to understand. The universe is expanding at a rate that matches a vacuum energy of near zero, when every calculation says it should be so massive that space itself would have curled into a singularity the moment after the Big Bang. So the question no one can answer is simple. What's canceling out the energy? What's keeping the vacuum from boiling the universe into nothing? Number 9. The lithium problem. In the first 20 minutes after the Big Bang, the universe was a nuclear furnace. Temperatures and densities were so extreme that protons and neutrons fused into the lightest elements, hydrogen, helium, and a small amount of lithium. This process, called Big Bang nucleosynthesis, is one of the most precisely tested theories in cosmology. We can model the conditions, run the numbers, and predict exactly how much lithium should exist in the early universe. And when we look at the oldest, most pristine stars in the Milky Way, stars that formed from gas untouched by later stellar generations, we find a consistent problem. The measured lithium abundance is about 3 times lower than the model predicts, not slightly off by a factor that violates the standard model of cosmology. For decades, astrophysicists have tried to explain it away. Maybe stars destroy lithium more efficiently than we thought. Maybe we're not measuring it correctly. But observations keep tightening the noose. The lithium we see in these ancient stars is stubbornly, consistently too low, which means either our understanding of the first 20 minutes of cosmic history is incomplete, or there's a missing piece of physics, a new particle, a modified nuclear reaction rate, something that intervened in those first minutes and scrubbed the lithium clean. And if the most basic predictions of the Big Bang are wrong by a factor of 3, what else is wrong? Number 8. The Flyby anomaly. On January 23, 1990, NASA's Galileo spacecraft swung by Earth for a gravity assist. Engineers tracked its trajectory with atomic clock precision, accounting for every known force, Earth's gravity, the moon's tug, solar radiation pressure, even the tiny push from thermal radiation emitted by the spacecraft itself. And when they did the final accounting, Galileo was moving slightly faster than it should have been. The difference was tiny, about 3.9 millimeters per second. But it was real, and it wasn't an isolated incident. In 1998, the Near spacecraft did another Earth flyby and emerged with an unexplained velocity increase of 13.5 millimeters per second. In 2005, Rosetta swung by and picked up 1.8 millimeters per second. In 2007, the same spacecraft made another pass and again deviated. The pattern is consistent across 5 different missions. There's no known force that can explain it. Gravitational models are precise to parts per billion. Solar radiation pressure is accounted for. even general relativistic effects are included. And yet, every time a spacecraft uses Earth for a gravity assist, it comes out moving as if it received an extra unmodeled push. The effect is so persistent and so inexplicable that some researchers have proposed modifications to general relativity itself to account for it. Others think we might be seeing the first evidence of dark matter interactions with normal matter. But here's what no one talks about. We've been sending probes past Earth for decades, and every single time the laws of gravity break in exactly the same way. Either we've missed something fundamental about how gravity works at planetary scales, or Earth itself is doing something to passing objects that our physics cannot describe. Number 7. The axis of evil. The universe, cosmologists say, should look the same in every direction. That's the cosmological principle, the assumption that underpins everything from the Big Bang to dark energy. On the largest scales, matter should be distributed uniformly, and for the most part, when we map the cosmic microwave background, the afterglow of the Big Bang, it appears almost perfectly uniform. Almost. In 2005, researchers analyzing data from the UMAP satellite discovered something that should not exist. The largest scale fluctuations in the cosmic microwave background are not randomly distributed. They are aligned. Not just slightly, they align with the plane of the solar system and with the direction of Earth's motion through space. Statistically, the odds of this happening by chance are less than 1 in 1,000. The alignment was dubbed the axis of evil, and it's been confirmed by subsequent data from the Planck satellite. It means that on the very largest scales, scales larger than the observable universe's structure, the universe has a preferred direction. That violates the cosmological principle. It violates the Copernican assumption that we are not in a special place. And if the universe has an axis, if the largest patterns in existence are aligned with our solar system, then either we live in a universe that is fundamentally anisotropic, which breaks the standard model of cosmology, or we are in fact at a special location, not just in our galaxy, not just in our local group, but at the precise center of a cosmic alignment that physics says has no business existing. Number 6. The Kuiper Cliff. Beyond Neptune lies a region of icy bodies called the Kuiper Belt. For decades, astronomers assumed it extended outward with a gradual decline in objects, like the asteroid belt, but much larger. In 1997, when the first deep surveys of the outer solar system were completed, they found something else entirely. The number of objects drops off a cliff at about 50 astronomical units, 50 times the Earth-Sun distance. Not a gradual decline. A sudden, dramatic disappearance. There's no known mechanism in planetary formation that can produce such a sharp boundary. Models of solar system formation suggest the Kuiper Belt should extend smoothly for hundreds of astronomical units, with objects thinning out slowly over distance. Instead, we see a wall. The only natural explanation is that something swept through the outer solar system and cleared out everything beyond that distance. But there's nothing there now. No massive planet, no stellar flyby remnant, no dark object with enough gravitational influence to sculpt such a precise edge. The leading hypothesis is that a yet undiscovered planet, sometimes called Planet 9, might be responsible. But even Planet 9, with a mass several times Earth's, can't create a cliff that sharp unless it migrated through the early solar system in a very specific way, which means either there's an object out there far larger than anything we've found in the outer solar system, or the Kuiper Cliff is evidence of something far stranger, a gravitational anomaly, a boundary in space itself, or a scar left over from a cataclysm our models never predicted. Number 5. The WOW. Signal. On August 15, 1977, astronomer Jerry Eman was reviewing data from Ohio State University's Big Ear radio telescope when he saw something that made him circle it in red pen and write a single word, WOW. The telescope had detected a narrowband radio signal at 1420 MHz, the hydrogen line, the exact frequency where any intelligent civilization trying to communicate might broadcast. The signal lasted 72 seconds, the maximum time the telescope's rotation could track a fixed point in the sky. It was 30 times louder than the background noise, and it had all the hallmarks of a non-terrestrial, non-solar system source. It came from the direction of the constellation Sagittarius. No known natural phenomenon produces a narrowband signal at that frequency. Pulsars don't. Quasars don't. Even the most exotic astrophysical objects produce broad spectra. This was something else, and it never repeated. Despite decades of follow-up observations with more sensitive instruments, pointed at the exact same coordinates, at the same frequency, at the same time of year? Nothing. The silence is the problem. If it were a natural phenomenon, it should have been observed again. If it were a one-time cosmic event, it should have left some residual signature. If it were a terrestrial interference, it shouldn't have moved with the sidereal rotation of the Earth, locking on to a fixed point in space. The WOW signal remains the strongest candidate for an extraterrestrial transmission ever detected, and its refusal to repeat is in some ways more disturbing than if it had, because it means something out there broadcast a deliberate, powerful, narrowband signal at the exact frequency of hydrogen, the universal communication standard, for exactly one 72-second window, and then went silent. Either we caught the only transmission from a civilization that vanished, or something wanted us to know it was there, once, and then chose not to confirm. Number 4. The CMB cold spot. When the Planck satellite mapped the cosmic microwave background with unprecedented precision, most of the tiny temperature fluctuations looked exactly as theory predicted, random, Gaussian, consistent with quantum fluctuations amplified by inflation. But there's one region that doesn't fit. A large patch of sky in the constellation Eridanus is significantly colder than the surrounding background. Not just a statistical fluke, it's about 70 microkelvin colder, across a region nearly 10 degrees wide. That's enormous. If the universe is isotropic and homogeneous, the odds of a fluctuation this size occurring by chance are less than 1 in 50,000. For years, astrophysicists tried to explain it as a foreground contaminant, dust in our own galaxy, or the integrated Sachs-Wolf effect from a vast cosmic void. But deeper surveys have ruled out a void large enough to produce the effect. The cold spot is real. It's a patch of the early universe that was fundamentally different from everywhere else. One hypothesis is that it's a shadow, a region where the cosmic microwave background photons were absorbed or scattered by something between us and the surface of last scattering, but that would require a structure so massive it defies the scale of anything in the observable universe. Another hypothesis is that the cold spot is evidence of a collision with another universe. Some theoretical models of eternal inflation predict that bubble universes can form and occasionally collide, leaving circular imprints on the cosmic microwave background. The cold spot is the right shape, the right scale, the right temperature contrast, and if that's what it is, then the universe we live in isn't the only one. It's just one bubble in an endless multiverse, and what we're seeing is the scar from when we brushed up against another reality. Number 3. The Hubble tension. Since Edwin Hubble first measured the expansion rate of the universe in 1929, we've been refining the number. Today, we have 2 ways to measure it. The first uses the cosmic microwave background, the early universe. You take the Planck satellite's map of the primordial fluctuations, plug it into the standard model of cosmology, and you get an expansion rate of about 67.4 kilometers per second per megaparsec. The second uses the local universe, Cepheid variable stars and Type 1a supernovae, measured by the Hubble Space Telescope and now the James Webb Space Telescope. That method gives you about 73 kilometers per second per megaparsec. These 2 numbers do not overlap. Their error bars don't touch. The discrepancy is 5 sigma, the threshold for a formal discovery in physics. It means there is a less than 1 in a million chance that this difference is due to random error. Something is wrong. Either the early universe measurements are biased, the local universe measurements are biased, or the standard model of cosmology, the lambda CDM model that has been the foundation of modern cosmology for decades, is incomplete. The tension has only grown with more precise data, and the most exciting possibility is that it points to new physics, something like early dark energy, or a modified theory of gravity, or a new relativistic particle that existed in the early universe but has since decayed. But the part that should concern you is this. The 2 most precise measurements we have of the universe's most fundamental property, how fast it's expanding, contradict each other. And if we can't measure the expansion rate of the universe with 2 independent methods, what else are we getting wrong about the history of everything? Number 2. The quantum eraser. In quantum mechanics, there's an experiment so strange that it forces you to confront whether reality exists when you're not looking at it. The double slit experiment is famous. Fire a single photon at a barrier with 2 slits, and it behaves like a wave, interfering with itself. Place a detector at one slit to see which path it takes, and it behaves like a particle. The interference pattern vanishes. The act of observation collapses the wave function. That's strange enough. But in 1982, physicists Marlan Scully and Kai Darkschel proposed a variation called the quantum eraser. You send a photon through the double slit, and you entangle it with another photon, a witch path marker. The marker tells you which slit the first photon went through. The interference pattern disappears. But here's where it breaks reality. If you then erase the witch path information by measuring the marker photon in a way that destroys the information about which slit the first photon took, the interference pattern reappears. Even if you erase the information after the first photon has already hit the detector. In later versions of the experiment, performed by Yoon-Ho Kim and others in 1999, the decision to erase or not erase the witch path information was made after the photon had already been detected. The results showed that the interference pattern was determined by whether the information was later erased. Not by a cause preceding an effect, but by a future event reaching back and deciding the past. This isn't interpretation. This is experimental data. It means the timeline of cause and effect at the quantum level is not fixed. An observation now can determine whether a particle behaved like a wave or a particle at an earlier moment. And if that's true for photons, what about the universe? What about the entire cosmic history? If a quantum eraser can retroactively determine the state of a single particle, then the idea of a single, objective past, the idea that the universe has one history, is an illusion. And that connects directly to the first item on this list, the one that forced physicists to ask whether reality itself is locally real. Number 1. The violation of Bell's inequality. In 1964, physicist John Bell devised a mathematical inequality that put a hard limit on what local hidden variable theories could predict. If the world is locally real, meaning objects have definite properties independent of measurement and no influence travels faster than light, then certain correlations between entangled particles cannot exceed a specific value. For decades, the experiments kept pushing closer to the limit, but in 2015, the first loophole-free Bell tests were conducted. Ronald Hansen at Delft University of Technology and later groups at MIT, NIST, and the University of Vienna closed the detection loophole, the locality loophole, and the freedom of choice loophole simultaneously. The results were unambiguous. The correlations exceeded Bell's inequality by 5 standard deviations. The world is not locally real. That's not a metaphor. That's not a philosophical interpretation. That is a statement about the fundamental structure of reality. There are no hidden variables that determine the properties of particles before they're measured. The moon, as Einstein put it, is not demonstrably there when no one is looking, and influences between entangled particles, what Einstein called spooky action at a distance, are instantaneous, not limited by the speed of light, not mediated by any known field. The universe, at its most fundamental level, is non-local. It does not have definite properties until they are observed, and information can travel faster than light, at least in the sense that the correlations between particles violate any possible local explanation. This is the finding that underpins everything else on this list. The vacuum catastrophe, the lithium problem, the Flyby anomaly, the axis of evil, the Kuiper cliff, the WOW, signal, the cold spot, the Hubble tension, the quantum eraser, all of them are symptoms of a deeper truth. They're not anomalies. They're consequences. Because if the universe isn't locally real, if properties don't exist until measured, if influences aren't bound by light speed causality, then the very idea of a universe as a single, consistent, deterministic history is a human projection. What we call physics isn't a description of a pre-existing reality. It's a set of constraints on what we can observe. And the fact that we exist at all, that we can stand here and measure these contradictions, isn't a problem to be solved. It's the inevitable result of a reality that doesn't take shape until something, or someone, asks,